Hi, online class. We're doing a couple of examples from chapter 9. These are on page 447. It's in the summary section. So you'll see again in the homework, you've got chapter 9, 10, and 11. There are sections there that just scramble everything up, so you have to go through and pick the correct method of analysis. Those are really good sections to practice, okay? So you'll see those in your homework. So we're talking about number 12 here. It says, from a Harris poll, 881 of 1,013 randomly selected adults said that they always wear seatbelts. Construct and interpret a 98% confidence interval for the proportion of adults who always wear seatbelts. Okay, so we determined that we want a confidence interval, 98%. We're talking about which function in the calculator to use. So if you use Z or T interval, you're estimating a mean, okay? Z interval is number 7 on your test menu. T interval is number 8. So if you want to estimate a proportion, you got to go down to one proportion Z interval. You guys with me? Does that make sense? Okay. Sometimes too it'll help, like if you go down to Z interval and you go, okay, well, it's asking me for sigma. Do I see a sigma in there? Do I see anything at all about a mean? No, not really. Okay, so regroup and, ask yourself some questions. The stuff with proportions is really, it's just the least amount of information, just a very, all you need is the sample size and the number of successes within the sample. Yeah,
so
Lauren?
it's kind of like if it doesn't give you the certain ones for like the Z interval, you know automatically it's a T interval. Like, I'm getting confused with which one to use when.
Okay, with a Z or a T interval, numbers 7 and 8 on that menu, in each case you're estimating a mean. It'll say, find a confidence interval for the average, blah, blah, blah. Okay? So here, we want an interval for the proportion. So again, a Z interval is going to be number 7 on your test menu. T interval is number 8. And if you're estimating a proportion, go down further in your menu and you'll see one prop Z interval. Is that selection A in everybody's menu?
Yeah.
Yes.
Okay. Some of the calculators have more stuff on it, so I don't know if that falls on the end or whatever. So here you want selection A, which is a one prop, one proportion, right? Z interval. So if you are using a Z critical value or cutoff value, but again, you're estimating a proportion. Okay, is everyone okay with that? All right. Okay, so what is your sample size? How many?
1,013.
1,013. And how many successes in that 1013 trials? 881? Okay, excellent. And that's all you need. And we want a 98% confidence interval. Okay? And again, this is number 12. Okay, so go down to one prop Z interval, and you see all you need is your number of successes and your number of trials, and then your confidence level, 98%, and calculate, and you're good to go. So again, let me go through those steps. You're going to go down to one prop Z interval. You guys see it? Can you find it? Okay, everybody? Okay. And then when you go into that menu, the X wants your number of successes, the N is your sample size, or your sample or your number of trials, and then you type in the confidence level and you're good to go. So with the online students, I wanna make clear that we've been pretty much working from the calculator. You don't wanna do these calculations by hand because it's just nasty. Scott?
Do they want p hat or do they want the two numbers?
That's what I.
Well, what you want, okay, the output. Okay. So p hat, remember, p hat is x over n. It's the point estimate. That's the point estimate. And it's going to, the output is going to give you p hat. Remember, p hat is in the middle of the confidence interval. It's the point estimate for the proportion of all adults who always wear their seatbelt. Okay, but remember, how likely is it that the true population proportion is the exact same as that point estimate? Slim and none, right? We've established that. So again, what you want ultimately is to create that interval of values that you are 98% confident contains that parameter of interest. Okay, so let's say 3 decimal places, so 0.845 to 0.894. Okay, so there's our 98% confidence interval for the proportion of all adults who always wear their seatbelt. Okay, somebody tell me somebody interpret that for me. Can somebody try? Somebody want to? Kevin?
We are 98% confident that the proportion of people, of adults that always wear their seatbelt is between, what was the next one? Sorry, is between 0.845 and 0.894.
Absolutely perfect, perfect, perfect. Did you hear him? We are 98% confident that the proportion of all adults, because we're making an inference about the population, right? That's the whole plan. Who always wear their seatbelt is between 0.845 and 0.894. If you want to write this as percentages, you're welcome to do that. If it makes, if it helps it make more sense to you. Same thing, right? What do you think? We good? Okay. How about the second problem? Number 13. In a random sample of 100 estate tax returns that was audited by the IRS, it was determined that the mean amount of additional tax owed was $34.21. Assuming that the population standard deviation of the additional amount owed is 2583, construct and interpret a 90% confidence interval for the mean additional amount of tax owed for estate tax returns. What are we finding?
Wait, the population standard?
We're estimating a mean. Right, good. So let's do the what do I want to say? The flow chart. The flow chart that should be going through your brain. Okay? So we want to estimate a mean. And how are we going to do it?
Z interval?
What are we actually going to calculate? A blah blah blah. What? What are we going to do? What are we going to create? What are we going to calculate? A confidence interval. Perfect. We're going to do this by creating a what percent? 90%? A 90% confidence interval for mu. Okay. We have two choices, correct?
Yeah.
What are our two choices? Z interval or T interval? Which is it going to be? Why is it Z?
Because the standard deviation of the population.
Good, good. Okay, so we want a 90% confidence interval for the mean, okay? So we're going to estimate a mean, we're going to use a confidence interval. Then your next question is Z or T. So then you go to, what kind of standard deviation do you have? If the problem does not say population standard deviation or sigma equals, one or the other, you're going to use T. Okay? If it doesn't say it's a population standard deviation, do not make that assumption. Okay? So in this case, it does, so we use Z interval. You with me? Humor me. Say yes.
Yes.
Okay, thank you.
Is this all 9-3?
This is the Chapter 9 review. Z interval was 9-1 or 9-2? 9-1? 9-1?
9-1.
Okay, so we want a Z interval. We're going to use Z interval. And in our calculator, that's number 7 on the test menu. But we need to pull some information out. We need the sample size. We need the sample mean. And we've determined it's Z, so we have, we're going to have a sigma as well. What are those numbers?
100.
100 is the sample size. Good. What do we have for sample mean? 3421? Perfect. And our sigma is 2583? Perfect. Let's do it. So we go to okay, stat, right, down to Z interval. Standard deviation, oh shoot, no I can't read it, 2583. Mean is 3421. N is 100. Confidence level. You guys with me?
Okay.
Yeah.
For a quiz, for a test, how would we write that on our test? Would we just write in the random?
I will ask you which item on the test menu you used for the problem. Yeah. And then you guys can jot down if you want, just X bar equals, sigma equals, or S equals, N equals. You can just, take a little bitty amount of space and jot that down.
And then we're interpreting the problem, putting
Yes.
it into words?
Yes, exactly, Connor, yes. All right. Okay, so we got from 2996.1. So this is money, right? So it's like 2190 or 2996 and 10 cents.
Are we rounding up on this?
To say again?
Are we rounding up on this one?
You could go to the nearest dollar, or since it's money, I just decided to keep it in 2 decimal places.
Okay.
3845. In my math lab, it'll tell you, how it wants it rounded. 3845.90. Okay, so let's look back at the problem and think about what this is telling us. We're 90% confident that the mean amount of additional taxes owed for all estate tax returns in this case is between $2,996.10 and $3,845.90. Yeah? Cool. Good. All right. So if you guys want to go back and look over this, I'll be posting the link. Okay, so online students, we've been going over all the terminology associated with a hypothesis test. You'll find that in 10.1 and 10.2 and my notes from those sections. And we are actually, you'll find that I think this stuff comes together a lot easier when you actually start applying it. So last time we were in the process of conducting this hypothesis test, which you will find on page, it's number 28 on page 478. Number 28, page 478. So let's go through our steps. So step 1 was that we want to set up our hypotheses. So in the null, In the null, we have the established fact. So the null hypothesis, remember, we always assume to be true until we can prove something else. So that's where H1 comes in. It's like the challenger, right? So HO is like the champ, right? And H1 is like the challenger. And the champ's going to stay the champ until somebody else beats him, right? Right? You guys with me? So HO, we decided that it says the mean birth weight of all babies born in 2005 was 3270 grams. So that is the established fact from 2005, the last year that data were available. Okay, a random sample of 15 births to mothers who were less than 15 years of age results in a sample mean birth weight of 3080 grams. To conduct a hypothesis test, because the sample size is small, we discussed last time that the population of birth weights has got to be normally distributed, right? Because we have a small sample size. So the assumptions here are that, you guys tell me, what are the assumptions here? Go ahead, Scott.
Left-tailed test.
Okay. What has to be true about what's going on in the situation? Let me rephrase. To use this z-test that we're going to use right here. Okay, Emma?
Sigma is known. and
Sigma is known.
X bar is known.
And x bar is normal. Good. So our assumptions are like our criteria for using a specific inference method. And in this case, we have to have a known population standard deviation, and we have to have x bar normally distributed. Okay? So we discussed that the population of birth weights had to be normally distributed because we have a small sample size. Okay, so assuming that the requirement from Part A is satisfied, okay, does the evidence suggest that mothers less than 15 years of age have lower birth weight babies? So in the alternative, you're always going to have the same parameter or parameters, the same number, and the symbol is going to change based on what you want in the problem. Here it's lower birth weight babies. So what we're basically saying is for the group of mothers aged younger than 15, okay, is their mean baby birth weight the same as it is for all mothers, or is it significantly lower than that number? Okay? Is everyone clear? Is everyone all right with that? Okay, okay. So then we pull our information out of the problem. And you're right, Scott, this indicates that we have a left tail test. So we have a left tail test. Okay, so we have a sample size of 15. Our sample mean is 3080. Okay, and in Part B it says, assume that sigma is 610 grams. So you would have to read through the whole thing before you can determine your type of test. You can still set it up though, that's fine. And we've got a 0.10 level of significance. Okay. So this is the first problem for you guys online. This is the first problem in hypothesis testing that we're going to work through all together. And we discussed last time that there are actually 3 ways to test a hypothesis. This is what we're going to do right now is called the critical value approach. And then we're also going to look at the p-value approach, which is much more common. And we're going to also look at testing a hypothesis using a confidence interval. Kevin, did you have a question?
Yeah, what is that last one?
Oh, alpha is, is the notation for the level of significance. It's use a 10% level of significance. So that's just the notation for the significance level. Okay, so let's continue over here. Okay, don't let me forget to give you, Lab 6 is ready, it's up for you guys too online. And it's due when you come to take your final on Wednesday the 25th, okay? You've got 9.193 to do tonight. You guys, it's a little bit different. And I emailed you guys your take-home quiz. Don't let me forget to give you your take-home quiz before you leave, okay? Because I'm on a roll. We've got to finish the problem. Okay. So step 1, you set up your hypotheses. Step 2, you pull all your other information out of the problem. We determine this is a z-test. Because it has to do with means, and there's the population standard deviation. Okay? Now, let's do this in the by hand method, which is really, it's kind of like prehistoric, but it kind of helps you understand the whole process. Okay, so we're going to do a left tail test. So this would be step, what are we on? Step 3? Step 3 is we're going to set up our graph. Okay, so the established mean is, again, it's the champ until we can prove something different. The level of significance goes in the appropriate tail. If you're dealing with a two-tailed test, you would chop the level of significance in half and put half in each tail. So what we're saying is, with this level of significance is, we're willing to risk, well, let me put it another way. We're willing to have a 10% chance that this is the true mean, but we reject it anyway. Right? It's a type 1 error. It's the probability of making a type 1 error. So we're willing to take a 10% risk that the true mean is really, really close to the 3270, but we reject it anyway. Okay, you with me? Okay. So, next step is we find our critical value. So our critical value is the demarcation point between our rejection region. So if our test statistic falls out here, we're going to reject HO. Bless you. And if our test statistic falls in the rest of the distribution, we're going to not reject HO. Bless you. HO, remember, is always, everything is based on HO and what HO is. So it's always in terms of HO. Okay, so our critical value, the easiest way to find that is you can take a copy of your t-table. The bottom row of your t-table is z-scores. So look at 10% in a tail. So use your t-table, go 10%, go all the way to the bottom, and you've got 1.282. Yeah? So remember, each line of your t-table is a different t-distribution, and then when the sample size gets really, really, really big, the t-distribution and the z are virtually indistinguishable. So as your sample size increases, as it gets really big, you might as well just use z, is what they're saying. So 10%, z-score, 1.282, and because it's on the left-hand side of the distribution, it gets a negative. 2. Okay. So the deal is, if our sample mean is within 1.282 standard deviations below the hypothesized mean, we're not going to reject HO. If it's more than 1.282 standard deviations below the hypothesized mean, we'll say it's too far away to be called same, and we'll reject HO in favor of the alternative. Okay? You guys with me? Okay, so now the next step is we calculate our test statistic. So we find out exactly how far away the sample value is from the hypothesized mean. Okay, So we've got x bar minus mu over sigma divided by root n. So every hypothesis test has hypotheses. Every hypothesis test has sample data. Every hypothesis test has a test statistic. They don't always have a critical value. That's only for the critical value approach. Okay? But they always have a test statistic. So in our case, we're going to take the sample mean, which is the 3080, subtract the hypothesized mean. So this is the hypothesized mean. It is what we consider to be the true mean, again, until we can prove something different. So that's the 3270 divided by sigma, which is 610, over root 15. Okay, so let's calculate that. So again, what this does, what the test statistic does, is tell us how far away this sample mean is from the hypothesized mean. Okay? In terms of standard deviations. Yeah, Lauren. How far away, okay, the test statistic always tells us how far away our sample statistic is from the hypothesized value, whether it be a proportion or mean or whatever, in terms of standard deviations. Okay. Anybody have that? What'd you get, Kevin?
Negative 1.206.
Negative 1.206. Anyone agree?
Yes.
Good. So our sample mean is 1.206 standard deviations below the hypothesized mean. So your hypothesized mean is the original distribution, the critical value and the test statistic are all in terms of z. Okay, 1.206. Ooh, pretty close, huh? But what do you think? Is it in the rejection or in the non-rejection region? It's in the non, isn't it? Okay, so, but it's close. It's like something like there. So there's our test statistic of negative 1.206. So with the critical value method, what you're doing is comparing the locations of the critical value in the test statistic. You start with your alpha, put it in the tail or tails, find your critical value, and then where does the test statistic lie in relationship to that critical value? You guys with me? Okay. So here, and again, that's step 4. So here, our test statistic is in the do not reject region. So this is what I want you guys to do. I'm going to ask you for an initial conclusion. So that would be step 5. In the initial conclusion, I want you to tell me whether you're going to reject HO or not reject HO, one or the other, only. So we are not going to reject HO. And then I'm going to ask you for a final conclusion. And in the final conclusion, I want you to write me something that makes sense with respect to what you just found and the problem. You with me? Maybe not yet, but you will be. So you might want to think about these things as you're doing homework problems, okay? So what are we going to say? Go back to the question. Does the evidence suggest that mothers less than 15 years of age have lower birth weight babies? The evidence does not suggest that mothers less than 15 years of age have lower birth weight babies. And that's all you got to write. You with me? Okay. The evidence, because again, what you determine is solely based on your evidence, which is your sample data. Okay? The evidence does not suggest that mothers, what is it, mothers less than 15 years of age have lower birth weight babies. And again, we're talking significantly lower. Okay, you guys cool with that? Yeah, Scott?
When you're doing the calculation of the TS,
Test statistic?
what's the best way to input that, like the order? Because I can't get the same thing.
Oh, okay, so how do we get this to go here? Okay, let's work on that. I do it in 2 steps.
You do?
Either that or you gotta use parens for both the numerator and the denominator.
Because if you do it all like that, you get it.
Yeah, so I would go 3080 minus 3270. Yeah, it's definitely an order of operations thing. And then go divided by, and you want to group your denominator. So you've got 610 divided by root 15, was it? Yeah. Close the root, close the denominator. So be careful with that, the double paren there. I want to make sure and get a double paren. And there you go. Cool. Okay, so calcium is essential to tree growth because it promotes the formation of wood and maintains cell walls. In 1990, the concentration of calcium in precipitation in, I'm not even going to try to pronounce it. Anybody from New York can pronounce that? I can't. Was 0.11 milligrams per liter. Okay, a random sample of 10 precipitation dates in 2007 results in the following data. All right. Because the sample size is small, we must verify that calcium concentrations are normally distributed and the sample does not have any outlier. Okay, I won't ask you about the outlier thing. A normal probability plot and box plot are shown. Are the conditions for conducting the hypothesis test satisfied? You know, and I wouldn't count on a box plot because with a small sample, that's the point. Box plot isn't supposed to be accurate. So we'll consider those things satisfied. And so does the sample evidence suggest that calcium concentrations have changed since 1990? Assume that sigma is 0.08 and use the 0.05 level of significance. This is a perfect problem to segue into the next method of hypothesis testing. Okay. So everything, your setup and all this stays the same. Okay? So we'll keep this for right now. Our first step is to set up our hypotheses, and that is still the case. Okay? So in 1990, the concentration of calcium in precipitation was 0.11 milligrams. Okay, and when they give you they're not saying on average, but technically you're supposed to assume that it means on average. Okay? So what is our HO? What's the established fact?
0.11 milligrams.
That the mean calcium in precipitation was 0.11 milligrams. So in your alternative, you have same parameter, same number. You're just looking at how you want to compare. Okay, this is good. Your sample. And at the end of this problem, it says, does sample evidence suggest that calcium concentrations have changed since 1990? What is going to be the inequality there? Not equal, good. So you're not looking for, that's a pitiful mew. You're not looking for the change to be significantly greater or smaller. You're just looking at for some change in some way. Okay? So there's your step one. Your step 2 is you're going to go back into the problem and pull out all the sample data. So here we want a sample size, a sample mean, and they give us that the population standard deviation is 0.08. Okay, so what's our n? 2, 4, 6, 8, 10? Can anybody get an X bar out of that? And then we'll go back and do this. I'll show you this one by hand, and then we'll do it by calculator.
How do you get 0.08?
Oh, it's given way at the end.
Oh, wait.
Yeah, it's way at the end. It says, after the question, assume that sigma is 0.08 and use alpha equals 0.05 level of significance. So when I write, you'll see on next week's quiz, when I write out a hypothesis test, I'll give you little lines to write everything. I'll write HO equals, and you fill this in. H1 equals, you fill that in. And I'll ask you for N, X bars, standard deviation, sigma. I'll ask you, and I'll give you little spaces. I want you to write it all down, pull it out of the problem, okay?
X bar 0.1568.
0.15,
68.
6,
68.
68. Yes, Scott?
What were the keywords you used to find not equal to?
Oh, okay. Can anyone else verify that mean first? Is that right?
Yeah.
Okay, cool, great, thank you. Okay, so at the end it says, so here's the question. Does the sample data or sample evidence suggest that calcium concentrations have changed? Otherwise they would have said had decreased or had increased. But when you're just looking for change in either direction, you're going to use a not equal. Does that make sense? So type of test, right tail, left tail, two tail? Two tail because of the not equal. Okay, so that's step 2. Step 3, we're going to set up our graph. The mean is assumed to be 0.11. We've got a two-tailed test because of the not equal sign in the alternative. We're going to take our alpha and now chop it in half and put half of that in each tail. And so with a two-tailed test, you're going to have 2 critical values. So again, that's the distribution of X bar. You're going to look into the distribution of Z. And your critical values, look at 0.025 in a tail in your T table. Go all the way to the bottom. And I've got 1.96. Does that make sense? Okay, so remember you can also use inverse norm and plug in to find the critical values and plug in how much probability is in that left tail. You'll get the left critical value and then you just find the other one by symmetry. Everybody cool? Yeah, Mike.
How did you get, you looked up the T-score for 0.11 to get the critical value?
You just look for the probability in the tail.
Okay.
So, got it? Yeah, because in the T distribution, again, you're just finding the area in that tail, and you just go all the way to the bottom for a Z-score. Okie dokie. Next step is our test statistic. New color. So our test statistic is a z-score. Back up. So it is x bar minus mu over sigma divided by root n for a z-test. So take your sample mean, subtract your hypothesized mean. So again, for the mean, you always look into the established mean, you always look into the hypotheses, and then divide by sigma divided by root n. And what do we get? And it's good to work these things through in class so you see if you're not getting the right test statistic. It's really important. And you guys online too, make sure that you're working these calculations through as you watch. And you know you guys can zoom through, you don't have to listen to the whole lecture. If there's this piece you want to reiterate, you can just take the little thing and drag it and get to whatever part you want to review. What do we get? 1.85, Mark? Anyone agree? Yeah? No?
Yeah.
Yeah? Okay. Sorry? Got it? Okay. So now we're going to compare the location of the test statistic with the location of the critical values. Okay? So the test statistic is going to fall, remember in a standard normal, the mean is 0. 1.85 is going to fall real close to this critical value, but still within the do not reject region. You agree?
Yeah.
Is everyone okay with that? So here's our test statistic of 1.85, and our initial conclusion is going to be what?
Do not reject.
Do not reject. And you never reject or do not reject H1. It's always in terms of HO. Do not reject HO. And then let's go back to our question. Is it up here? Oh yeah, it is. What are you going to write for your final conclusion? Does the sample evidence suggest that calcium concentrations have changed? If we do not reject HO, then what are the calcium concentrations about? They're about the same as they were before, right? So have they changed? No. So you could write that the sample evidence suggests that calcium concentrations have not changed since 1990. And it would be, of course, in the sample region. What do you think? Does this make sense? Okay, before we go to the second way to look at a hypothesis test, I want to actually look at the third way. Confidence intervals.
Did we try this on the calculator?
Oh, and we can do this on the calculator. You're right, Erica. Okay, so in your calculator, to do a hypothesis test, okay, this thing is called a z-test. It's in the tests menu. So the first part of the menu here is all hypothesis tests. The second half is all confidence intervals. So you would choose number 1, z-test. And you can run a test off of data. So if you went over and chose data, you could put all that data in a list, and run the hypothesis tests off of the data, which we'll practice sometime next week or something. Mu naught is the number in your hypotheses. It's the established mean. Sigma, 0.08. X bar, 0.1568. Sample size is 10. So if you're using data in this case, you wouldn't have to plug in the X bar or the N. The calculator would pull that out of your data. Then the next line, okay, so this line is the symbol. You want to choose the symbol in the alternative. Okay, because it determines what type of test you have. You with me? Okay. We had not equal, and then you go down to calculate, and there you go. So your test statistic, 1.85, which we got, and then you would compare it to your critical values and make your decision. Okay, but like I said, is this clear? Is this all right? Yes, Scott.
Where are you using your critical values?
I'm sorry?
Are you, you don't take your critical values and put them into like step 4 at all?
The calculator does not include step 3.
Yeah.
Okay? Or really step 4, although it does contain the outcome. Because the calculator works off the p-value method, which is our other way of looking at a test I'm going to show you in a minute. Okay?
Yeah, but where do you use the critical values? Like,
Where do we, oh, in what we just did? Or you mean on the calculator?
Never mind, it's okay. Go
Okay.
ahead.
Okay, think about it, let me know.
Yeah.
Yeah.
Can I get my test or quiz?
Oh, you gotta go, huh? You bet. Okay, so then you would take your Z, here it's a Z-score, right? Your test statistic is a Z-score. So under a hypothesis test, it'll always reiterate the alternative hypothesis. Then it'll give you the test statistic. It's not going to call it a test statistic. It's going to call it a z-score or a t-value or whatever type of test you have. Okay? But it's always that next line. Then it'll reiterate some sample statistics. And the p-value is the method that we're getting to in the next, like I said, in just a minute. Okay, but first, let's go back to our hypotheses. It was mu equals 0.11 versus the alternative mu is not equal to 0.11. Correct? Okay, so do me a favor. Calculate, okay, remember, same assumptions here. You've got a known population standard deviation. You've got a normally distributed X bar. Calculate a Z interval, okay? Let's make it 95%. So give me a 95% confidence interval for the true mean calcium concentration. Let's say 90%. 95%? Okay, hopefully everybody has this. I'm going to erase it. I'll reiterate our Okay, so we're 95% confident that the population mean calcium concentration is between what two numbers? What do you get? You're going to use Z interval. What do you get?
0.107
0.107?
and 0.206.
0.206. Okay, so tell me this. If we're 95% confident that the true mean is in there, is 0.11 in that confidence interval?
Yeah.
Okay, so listen up, this is important. If we're 95% confident that the true mean in there, and the 0.11 is in there, then isn't it pretty likely that 0.11 is really, really close to being the true mean? So based on your confidence interval, are you going to reject HO?
No.
No, because 0.11 is in that interval. Does that make sense? Does that make sense? So that's the third way to calculate, to look at a hypothesis test. See, you already got it. Jennifer? Okay. Scott?
If you were looking at it like visually, would that be a two-tailed test? Like,
Oh, and that was a not equal. Sorry?
would that be like,
What you're doing is just seeing if this number lies within the interval. In a test of one parameter, you're always testing against a number, the established mean or proportion, okay? When you test two parameters, which we'll get to in chapter 11, you're testing them against each other. You with me? Okay, but for right now, and I want to keep reiterating that, so hopefully it just starts to sink in there a little bit. So right now, we're looking for that number. And if that number is in your confidence interval, then you would not reject HO because mu of 0.11, which is HO, is in the interval. That make sense? Okay, good, good. Now, if the interval did not contain 0.11, then you would reject. Right. You guys okay with that? Yes, Shantez?
You can only do that if it gives you a confidence interval though?
Well, I would be very likely to give you that question and then ask you to set up the hypothesis and then ask you to create a confidence interval and then say, based on the confidence interval, do you reject or not reject?
Did that come before it gave a confidence interval though?
No,
Oh, okay.
no. So that's actually, remember, that's the third way of looking at a hypothesis test. You can do it through a confidence interval. They kind of work hand in hand together like that. So every hypothesis test that we do has a sister confidence interval that goes with it. For a Z test, we have Z interval. For a T test, we have T interval. Yeah, good. For a one proportion Z interval, we have one proportion Z test, so on and so forth. Okay, so third way of looking at a hypothesis test. Okay. Do you agree? Let's go back to our example down there. That was the baby weight problem, I think, right? Now, do you agree that the 1.206 is really darn close to the negative 1.282? It's really close. But our result didn't say that. Our result just said, do not reject HO. So if the researcher just presented that information, do not reject HO, well then we don't really know how close the critical value sits to the test statistic, and vice versa. The test statistic could be really, really darn close. We would still not reject, right? It could be anywhere within this region, we would still not reject. So the second way of looking at a hypothesis test is called the p-value method. in the traditional or critical value method, you're comparing the critical value and the test statistic. In the p-value method, you're comparing the probabilities. You're comparing your alpha of 0.10, which sets your critical value, right? You're comparing that probability to what's called the p-value. And the p-value would be the probability beyond the test statistic. So the p-value corresponds to the test statistic like alpha does to the critical value. But instead of comparing the critical value and the test statistic, now you're comparing the alpha and the p-value. Okay? So the p-value is the probability that you get a test statistic more extreme, meaning toward the tail, than the one observed. So whereas reject or don't reject doesn't tell us how close of an outcome we had. The p-value will tell you exactly what's the probability that the mean birth weight of mothers under 15 is more extreme than the one you saw. Okay? How much more likely would it have been to reject HO? Okay, let me look at my notes real quick. Okay, so when you're calculating a p-value, let me back up. So the critical value approach, you compare the test statistic and the critical value. And again, these are both T's or Z's. In the p-value approach, you compare the p-value and the significance level. Which are both probabilities. So these guys are probabilities. These guys are Z or T values. So the p-value approach is what you're going to see, and I don't, realistically, most of you are never going to have to, do major research where you're, doing this stuff all the time. But you will probably be reading information, according to your subject of interest, whatever it is, education, medicine, whatever. You're going to be given results in terms of confidence intervals, p-values. That's what you're going to see, and that's what you really need to understand, okay? So when you calculate a p-value, let me back up. So in summary, when the p-value is less than alpha, you reject HO. Because what it's saying is, and this thing is a mess, but what it's saying is that the test statistic is pushed way far into the tail. And the area beyond it is really small. And when that happens, you're in the rejection region. You reject HO. And when the p-value is greater than, actually when it's less than or equal to, the chances that it's equal to is slim and none. When the p-value is greater than your significance level, you do not reject HO. Okay? When all the dust settles, that's the deal. So you don't draw the graph, you don't find your critical values, none of that. You just set up your test, run it through your calculator, get your p-value, and compare it to your alpha and make your conclusion, draw your conclusion. Some test likes that.
That's the easiest way, right?
Well, but you gotta understand what you're doing. You do have to understand what you're doing. Questions,
When
Kevin?
you find the p-values at the same you would find any other ordinary p-value?
You find the p-values just like you would find any probability. Any probability. Your table.
Oh,
Your table.
right.
Yeah. So, okay. Here's your test statistic. Let's round this to 2 decimal places. It'd be negative 1.21. Okay, so all that red stuff, sorry, that's such a mess. So all that red stuff is your p-value. Look up on your z table, right? This is a z distribution. Look up negative 1.21 and you'll give you your p-value. Excuse me a minute.
So you still find your test statistic, right? Either way, you still find your test statistic. The only difference is that you're not
Yes.
using your critical value here.
Yes, thank you. So Kevin says you still find your test statistic, which yes, you would. Because you have to find the probability beyond it. Now be really careful. The setup in your test is crucial in finding the right test statistic. Or, I'm sorry, the right p-value. Because let's say you have, let's say you have a test statistic of, I don't know, 1.28. Okay. Now in your H1, if you put, if you have a right tail test, say 1.28 is like here. For a right tail test, here's your p-value. If in H1 you put a left tail test, here's your p-value. So setting up your test correctly is crucial. And then, if you have a two-tailed test, so in H1, if you have a not equal, say your test statistic is 1.28 still, your p-value is the probability of getting something more extreme in either direction. There's your p-value. Does that make sense? The probability of getting a value more extreme than the one you observed. More extreme in the right hand, in the right direction, in the left direction, or in both, and it adds them together and that becomes your p-value. That make sense? Kevin?
So in a way, if you're looking for the p-value for not equal to,
For a two-tailed test?
yeah, you would take the left-hand side and multiply that by 2?
Yep.
Okay.
Yep, you have to add both pieces. Okay. Should we knock one out really quickly? A test using the p-value method? How about this? We use the p-value method and then we'll back it up with a confidence interval. Yes. Okay, so this is number 27. It's on page 478. Page 478. So real estate taxes are used to fund local education institutions, police protection, libraries, and other local public services. A household's real estate tax bill is based on the value of the house. In 2005, the mean real estate tax bill per $1,000 assessed value for all households in the United States was $11.38, with a standard deviation of 8.02. A random sample of 50 rural households results in a sample mean real estate bill per $1,000 assessed value of $11.09. Don't worry about part A. Do you believe that rural homes pay less real estate taxes per $1,000 of assessed value? Why or why not? Okay, so let's set this up. What's our established mean real estate value, tax value? It's per $1,000 assessed value. What is it? Was $11.38. Good. So the mean was $11.38 for all households. And so what we're doing is seeing if rural properties is pay what? Less taxes, more taxes, different taxes? Pay less real estate taxes per 1,000. So we have a left-tail test, not that we really care at this point. Okay, so now we need our sample statistics still. And notice here it says, in 2005, the mean real estate tax bill per $1,000 was $11.38 with a standard deviation of 802. It's not worded very well, but we're going to assume that that's the population standard deviation in this case. I would make sure and write population standard deviation. But they're saying that came from all of the data. Okay. What was our sample size? 50? Good. Sample mean? 1109. So now the sample statistic looks to be, it is definitely less than the mean, but again, it's all dependent on how the data is laid out, right? What the spread is. So this might be really close to 1138. It might be significantly below, but it's all based on variation. Okay? Whether it's significantly less or not. So what do we have as a significance level? Does it say?
No.
When it doesn't say 5%, you can just kind of assume. Okay, so let's do this in our calculator. So next week we're going to be busy, you guys. Now you've got all this stuff. We're going to finish up chapter 10, and we're going to go into tests of 2 parameters. Yeah, Lauren?
So how many sessions are we doing on the final?
Chapter 9 on. So what's mu naught here?
1138.
Good. It's the number in the hypotheses. Very good. Okay, and then we have our sigma. What was that? 11, no.
8.02.
8.02, thank you. And we have our x bar, 11.09. And we have our n. Okay, and then your symbol in the alternative. And remember that with the p-value method, it's crucial to find your correct p-value. You can't just take your cursor over to that icon. You have to hit enter and make sure you select it by darkening it. Okay, so we have a test statistic of negative 0.26. So our test statistic is negative 0.26. Do you see where I got it?
Yeah.
Okay, good. Our p-value is huge. When the p-value is bigger than alpha, what happens?
You don't reach.
You don't reject. And think about it. The sample value is like a quarter of a standard deviation away from the hypothesized mean. It's way close. So you're not going to call this significantly less, right? You with me? We're going to not reject HO. You can write, if you want, the p-value, or since the p-value is greater than alpha, do not reject HO. And then we'll go back and summarize by saying, do we believe that rural homes pay less real estate taxes? No. So final conclusion, yeah, according to our sample data,
Rural homes do not pay less real estate taxes per 1,000 assessed.
rural homes do not pay less taxes per $1,000 assessed value. Yay!